Welcome back, Precalcsters. In this video, we're going to try at least one time something a little bit different. So for this video, as discussed in class, you need to watch this, take notes on it, and we will work all examples with this material tomorrow in class together. So to start us off, we are beginning today Chapter 3, where we are going to focus on two different types of functions. We're going to be looking at exponential functions, and we'll write a more formal word here later, but exponential and logarithmic, or log functions, is the focus throughout Chapter 3. Now, in this chapter, there are only 5 sections, so this one's going to go fairly quick, but let's go ahead and dig in. In our first section, 3.1, again, we are just hitting the main material, the topics, concepts today in this video. Tomorrow in class, we'll have a chance to play around with these and actually dig in with some examples and things like that. But in 3.1, we are looking at exponential functions. And I don't normally do this, but I am going to rather, just make our definition right up here. Exponential functions. Okay, as we go through here, just so you know, exponential, this word is going to show up over and over and over and over. And the shorthand for this is just a capital EXP, and that's pretty much accepted everywhere. Now, worth mentioning, we have seen everything so far this year has been a form of algebra. Regular algebraic rules apply, nothing too crazy happens. With this, we will do our first little type of functions or family of functions, which we transcend all the regular algebra stuff. So just a nice little piece, these types of functions that require more than just the basics of algebra are known as transcendental functions. So let's go ahead, we're going to define this right off the bat, and then we'll dig in a little bit more. So definition wise, we're going to say exponential functions we'll define as follows. The function, the exponential, and again, right off the bat, here's that shorthand. The exponential function, which we're going to write the most basic of this as f of x equals a to the power of x, is read, and I'm just going to say is exponential, with base a. So the base, the number, whatever it is that we are going to connect our variable to, is an important idea. When we go through here, last little piece, we're just going to put on some requirements here. We're going to say, for this example, a, whatever our base happens to be, is going to be positive. We're going to require that it is not equal to 1. And then the last little piece, x, for our purposes, is going to be a real number. So no crazy powers with I or imaginary parts in the powers up above. Cool. This is the basic definition of these. So as we're going through here, our first main topic, we're just going to kind of connect these together. We'll start with just everything exponential. So exponential functions, and we don't need to define it here, but we have it. Cool. We know that they're all going to have this form, and it might get a little bit more complicated, but at its most basic, a base that is just some number raised to an exponent where there's a variable, and luckily it's x for us. So as we deal with these, the first little piece that I want to just kind of dig into is graph/evaluate. So nothing too crazy here winds up happening. We're going to make some rules here in class when we do this together. But at its most basic, we have 2 situations that we're possibly going to look for in this. Okay, step 1, if we want to evaluate it, I don't think we need to talk about it. We don't need to write it down. I'm just going to make a comment. Plug in whatever it is. So evaluating, if we're looking at this, and I know we're not going to do like a formal example here, but if you want to include it, we can fill this in tomorrow. If f of x is equal to, like, I don't know, 3 to the power of x, there's a couple things that wind up happening, and we'll dig into this. We're going to make a small table with some points and choose wisely what we use, but all I'm going to do is I'm going to leave this blank and we'll fill it in once we get here. And I'm going to make it like this. You should have this in your notes so that when we come in tomorrow to do this, we can graph this thing without any issue. We're going to do so by making a small table, x, and then we'll have a scratch work in the middle, and f of x right here. We will evaluate this one together tomorrow to make some generalizations or to verify some generalizations, but there's nothing too crazy that winds up happening with these. So what we will verify tomorrow with this example is there should be some kind of generalized ways that we can talk about these. So if we're graphing and evaluate, we'll see this happen here. And then underneath, we're just going to have generalized. So there's only going to be two situations that we'll possibly look at here. And for our first one, I'm going to have a small graph here. I suppose we'll do y equals a to the x for, and let's say we're going to pick an a greater than 1. And then over here, just in a slightly different color, we're going to also consider y equals a to the x for a this time where it's going to be greater than 0 because that's a requirement, but it's going to be less than 1. And we'll look at both of these examples. So as we're looking at this, if we have a is greater than 1, what we wind up seeing is that, and it doesn't matter what it is, we're always going to get the same general shape in this situation. So I'll switch back to, I'm going to use white for the background. Let's say that we have this graph, and these numbers will make more sense when we choose them in class as we actually work through the example, but we'll just think about some stuff. Easy numbers to always plug in. 0. If I plug in a to the 0, no matter what a is, as long as it's not 0, we get this ordered pair right here. Every single time on this parent function, we're going to get 0, 1, because any number to the 0 is 1. Now, this is weird to do, but I also like to plug in 1. So I'm just going to mark this off arbitrarily. If I were to plug in a 1 for the x value, it would just give me a to the power of 1, which winds up being a. If I plugged in a 2, I would get 2 comma a squared, and it just gets bigger and bigger. If I go the other direction and I try to plug in a negative 1, and I want to think about what happens here. At negative 1, my expression becomes a to the power of negative 1, which is 1 over a. And I see that I get a smaller number. This trend is going to continue. It might move or translate and change shapes a little bit, but the same general shape is always going to be true of exponentials, where they are going to take this form, where we see a couple important key features that are just going to keep showing up, and it's what makes these things so stinking useful to represent the natural world. Couple things. The domain of this function. There is not a single x value that breaks this, so we're just going to justify and check it out, all real numbers. Now, as we think about the range instead, the range of this function, let's think about what happens. On the right side, it goes up forever, and I can see that's going to keep happening. A to the 50 is not as big as a to the 100. On this side, however, let's just think about this. Even if I have something that's like a to the negative 1,000, and I can use a real number if this will make it easier. 2 to the negative 1,000 becomes 1 over 2 to the 1,000, which ridiculously large number in the denominator, but it's 1 out of that number, which is almost 0, but not quite, which means this thing is never, ever, ever in this form going to touch the x-axis. So for the range, we'll say it's a set of all y such that y is greater than 0. We can get arbitrarily close to it. We'll just never hit it. Okay. Other little pieces that I'm going to comment on. This thing is increasing everywhere. Now, there is fancy language that we can use if you want it. Just an alternative way. I'm not going to test you on this, but it's nice to have. Monotonic up. Everywhere this thing increases. As you move left to right, which is always how we read these, graph always gets bigger. Okay, for a to the negative x. We're going to do something similar, and I'll just have the same, roughly the same graph anyway, or same scale and axes is what I mean by that. And let's consider what happens. Once again, and I'm going to change this, and there's a couple ways we can think about it. I'm okay if we call it this since what we have written, but there's another way to think about these numbers, and we'll talk about this and clear that up in class. But let's just think about what happens. A is a smaller number, so if I think of something like 1/2, and this is all scratch work for me to think. If I plug in a 0, and it's 1/2 to the power of 0, same thing winds up happening. We're going to get the point 0, 1, which is super convenient. I'm going to highlight that, 0, 1. If I were to plug in a 1 into this example with 1/2, I would plug in a 1 and it spits out 1/2 to the first power, which is 1/2. So all of a sudden, what we see is this little thing where, man, this ordered pair is now 1 and 1/2. The negatives that we might pick start to make things a little bit wonky. If I were to take -1 and plug it in, if I did 1/2 to the -1, and I'm going to take some small steps here just to make sure it's clear. If I have 1/2 to the -1, exponent properties tell me, oh, this is 1 to the -1 over 2 to the -1. And then negative exponents just change where in your fraction things are. This winds up being 2 to the +1, because this just moves upstairs and becomes a positive exponent, over 1 to the +1. And I see that, gosh, I would get -1 and 2. Now, it's ugly to see it, but that's the same thing as me saying, oh, I would have gotten -1 and 1 over 1/2. But it's exactly what it is. If I go to -1, I get 1 over a, which because of our choice of a becomes a larger number. -1, sorry, and 1 over a again. This situation, if we run through these 3 points as best we can, something very similar happens with a noticeable, I think, fundamental difference. The domain of this guy is still all real numbers. Cool. The range here, still all y greater than 0. I'm going to switch this order a little bit. That's from 0 to infinity. I'm using set builder here instead. And then this thing we could say is monotonic down or decreases everywhere. Okay, so 2 different functions, same form, that just depend on our value of a that we look at. Now, these guys do have specific names. In yellow here, on the left, we get exponential growth. Unfortunately, I guess fortunately, depending on how you read this, unfortunately, we had a pandemic while we were all alive. Fortunately, we were all able to live through it. Looking at this, exponential growth showed up really commonly in pop culture stuff as soon as COVID hit. Really good job of modeling populations and disease. But we have exponential growth where as we move left to right, it's increasing. And then we also get exponential decay where as we move from left to right, instead of increasing, it is falling down or decaying. Cool. Exponential growth and exponential decay. Now, right off the bat, I'm not super concerned about graphing these yet. We will certainly graph them because, you know, it's Precalc and we're doing fancy algebra. But with both of these graphs, do not draw this. I'm just going to use gray. But notice, this horizontal line that I just drew only touches once. And this horizontal line only touches either function once. And this one only touches either function once. What we wind up seeing in our big kind of summative statement here, exponential functions are 1-to-1, 1-to-1, or injective is the fancy word for that. And the reason that this is significant is the fact that these things are injective, it implies an inverse exists. And more specifically, not just an inverse, but an inverse function exists. Okay, this is going to be like a real big part, and it turns out to be a really, really, really powerful tool. Okay, beyond this, we also get right off the bat, I'm going to try to make sure my colors match. I was using yellow before. Beyond this, when we're looking at exponential functions, we can graph and evaluate. It turns out that this idea of injectivity, one, it does mean that the inverse exists, which is a huge focus in here. But the other part of this is that we get this one-to-one property that we're going to use to solve all sorts of problems. So, last little thing that we're going to write today, I think the last little thing that we're going to write today is the following property. This one-to-one property, super duper useful. I can't stress it enough. And here it is. For any value of a that is greater than 1, we get a super, super nice idea. And I'm going to change that. I'm going to say any value of a greater than 0 and not equal to 1. Sorry about that. We have the following. Now, I'm going to intentionally skip a line because it's such an important idea. Here it is. A to the power of x. If we claim that it is equal to a to the power of y, this is true if and only if x equals y. This idea is the big one. Now, remember that this if and only if says that if I have the same base, and I'm going to go ahead and add that just a slightly different color. In this situation, to use it, we need the same base. If we have the same base and we have two exponents and I claim that they're equal, then the exponents must be equal. Alternatively, if you give me two numbers, x and y, that wind up being equal to each other, and you make that the exponent on some base, then the whole expressions wind up being equal to each other as well. So we're going to jump in with these tomorrow at the start of class. We'll look back at that graphing problem. I'm going to give you an example that if you come to class with these examples ready to roll, that will be super duper helpful. So I'm going to ask that we solve the following, and I'm going to use a little editing magic. All I need you to do is write down the problems. If you are feeling like adventurous and you want to try it, I would encourage you to do so. Solve it, if it's possible, for each of the following, and you'll see those right now. And here they are. Tomorrow, we will jump right in here looking at these examples and likely continue on, but this is our first little attempt just to see the realistic possibilities of flipping the classroom for this chapter. Okay, don't forget, make sure that if there's anything that I said, you put a note next to it in your notebook so you can ask questions at the start of class. And beyond that, I reserve the right, just so you guys are aware, to have a quick note quiz from the video at the start of each class to ensure that we're all watching this. So can't tell you it's going to happen, but very possible that you are going to be asked something very specific from these notes. So make sure that you have them down and clear. Other than that, let me know what you think. Smash that like button, and I will see you all in class tomorrow.